This video is going to be somewhat of a conclusion on the videos I've been giving on the subject of energy. So I call it the conclusions about energy. The study of energy started really as a result of the last 15 years study of gravity, in which it became obvious after about 5 years that gravity is caused by the conservation of energy and the conservation of momentum, of which energy is the more important. And then another 5 years to figure out how the conservation of energy and momentum can cause gravity to be observed. And then the last 5 years in figuring out how to describe this to others. And so I think I'm ready now to talk about it in conclusion, and also to include the equations I've spoken of before that I think should be used, something like these equations to be used instead of our existing equations, which do not, in the case of kinetic energy, do not include the mass of two bodies, although two bodies are involved in energy always, because energy is a property of the relationship between bodies. So let's start by talking about what is energy. Well, we know that if we take two bodies, and let's take the Earth and the Moon as examples, because they are bodies that we can see, bodies we know something about, and we know pretty much how they behave and how they have behaved. And so we're talking here not just in our imagination about what would happen if we did this or did that, but we can see how the Moon and the Earth relate to one another in terms of energy. And energy is, I believe, the most fundamental of all variables. We tend to think of energy as a function of mass, space and time, but in fact I think energy is more fundamental than that, and that space and time and mass are more components of energy, where the energy is that which was created first, as I've said before, at the beginning of the creation, when matter was caused to separate and possess energy in the form of light. So energy is very fundamental, and so I'm going to relate energy to separation, not just space, in this way, that there's a total energy between two bodies, and that this energy, it relates to the mass, not because mass causes gravity or causes energy in any way, but mass is a multiplication factor. It's somewhat of a dimensionless variable that you multiply by in order to get the total energy. So that if we know the energy between two individual particles, one in the Moon and one in the Earth, if we know the energy between them and we multiply by the product of the masses, we get the total number of lines of force, and therefore we get the total energy. I mentioned force because force is very closely related to energy. It is the rate of change of energy in space, or in distance. So the distance between the Earth and the Moon determines the energy per line of force, and the product of the masses gives you how many lines of force, and therefore the strength or the quantity of energy. Now, not only this, but the energy can exist in different ways. It's still energy, whether the energy is kinetic or whether it is potential. But we can break down energy into two parts, and I'm going to do it as vectors, not as straight lines, because potential and kinetic energy are different, but they're different in the way they're presented. They're both equal to the force times the mass, force times the distance. In the case of potential energy, it is the force times the distance in space between two bodies, integrated because the force varies. The kinetic energy is the force times the distance for which a body is accelerated, and then the energy remains with the velocity in what we call kinetic energy. But they're both related to lengths, and because they are equivalent to one another, kinetic energy and potential energy have an equivalence. The energy can appear as either. So I'm going to call this potential energy, and I'm going to put it in parentheses because it's not a direct measurement of the energy. It depends on it's not a linear relationship, for example. And I'm going to call this the kinetic energy. That separation there determines the kinetic energy, and this separation determines the total energy. So I'll put that down as the total E. So added as vectors, the potential energy and the kinetic energy totals the total energy. So this is the way in which we can, but both the equations for potential energy and for kinetic energy have to be similar, because they are both energy, they're both force times distance. There's no reason why they can't be similar equations, although they're not exactly the same, because they have different appearance. So let's get to the next stage, which is the model for developing the mathematical equations, because it's not as simple as this. There's movement as well as this static situation, although this implies there is some movement. And the moon is moving relative to the Earth. Even though it's going round the Earth, that is still kinetic energy associated with the Earth. The subject that I've discussed in some detail recently in regard to aircraft, that even though an aircraft is flying parallel to the Earth, its kinetic energy is relative to the Earth because it's in the same frame of reference. Similarly here. So we'll add those together, but first I'm going to describe the overall mathematical model. Now, the total energy between two bodies, which is the energy of between one unit here and one unit of mass here, multiplied by the product, giving you the total number of lines of force. That total energy, in the case of two bodies that are not touching, such as the moon and the Earth, is constant. And we tend to think that the energy is varying a lot between bodies, but it's not. The energy between the Earth and the moon has been the same since the moon last touched the Earth, which was over 4 billion years ago. So that's a constant. And so I'm going to draw this mathematically as a mathematical model with the Earth in the center of a circle, or more precisely in the center of a sphere, and the moon on the surface. So this distance here represents this distance here. Well, I'll put that down as representing the total energy, and that is the radius of that model of a sphere. I call it an energy shell because the moon has to stay on the surface of it so that its energy remains constant relative to the Earth at all times, whether it's going straight away from the Earth as it did originally or whether it's orbiting the Earth. It's still the same constant total energy, the vector sum of the potential energy and the kinetic energy. Now, there are many dimensions. There are 3 dimensions, for example, of space representing the potential energy, although you can express the separation as a single dimension. If we want to know more about direction of movement, you need to have the 3 dimensions of space. So there are 3 dimensions like this, and there are also 3 dimensions representing kinetic energy, because that can be in any of 3 dimensions, equivalent, representing the 3 dimensions of space. So there's 6 dimensions, and we've only got 3 available if that's an ordinary sphere. Now, a sphere does not have to be limited to 3 dimensions. In fact, there are 9, and I won't. The last 3, after 3 of these and 3 of these, are the 3 dimensions of the separation in time, which is associated with relativistic energy that Einstein described in his special theory. I'm not going to go into that, but there's a total of 9 dimensions. So in order to have a radius that represents 9 dimensions, we'd have to, we can only draw 3. You see, we can have the moon. Say the moon is going around in a circle like this on the surface of the sphere. That still only gives us 3 dimensions. So or actually we can have 2 dimensions of space here and 1 dimension representing kinetic energy. I've got to get a wiper here. I'm going to show you how you can have 9 dimensions for the radius of a sphere like this. And we do that if we say that is the total, this is the same as I had before, the total energy between the 2 bodies. You can separate that into potential energy and kinetic energy like this. These are not necessarily the same. They're only the same actually when the orbit is circular. So that is roughly what it's like now. But it does not have to be. If the moon were in a very, very eccentric elliptical orbit, then the potential energy then the length of these would be varying as the energy becomes less kinetic and more potential, or vice versa. So now we can now say this is potential energy. We can turn that into 3 dimensions by breaking this into 2. There's 2 dimensions of space, and we can break this into 2. So this can be R1, and this can be R2, and this can be R3. Now we've got 3 dimensions here, and kinetic energy is the same. We can break that into 2, and we can break this into 2, as long as that's a right angle. So this here, these are three dimensions of representing kinetic energy, and 3 here representing potential energy, and we can have 3 more representing time. So now if you use Pythagoras in each of these right-angled triangles, this squared plus this squared is that squared. This squared plus this squared is that squared. So if you do that, you find that that squared plus 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 that squared is equal to that. And that's how you can have, in this case, a 6-sided triangle. And you can have 12 sides. So that in order to add these, we say that the energy squared, or the length, the length representing the energy squared is equal to the sum of all the other sides, the 3 sides of space are there, and plus the sum of the 3 sides. This I call the x dimension, representing the where n is 1 to 3. 1 to 3, that's a plus sign there. So this is how we ended up, and I'll put down the actual equations more later. But that's how you can get what I call a crooked radius. The radius of that sphere is much longer if you were to follow its length. This length here, you see, is much longer than this. But when you add the squares, they're the same. This here, these 6 sides, 1, 2, 3, 6 sides, added as vectors have the same length as that. So that's the way that you can have a sphere that is has as many sides as you like. And in our case, we have 9 sides altogether, including time. Now, just a little more here. I'm going to give you the equations for this. Now I think I'll do that in a separate video because I must have run out of time. I'm only allowed to put up 15 minutes or so of videos. So that'll be enough for now. I'll do the equations themselves later when I do a final video. Thank you for watching.